Hello friends, this video on NEET dual nature of radiation and matter is brought to you by examfear.com. No more fear from exam. So let us do a quick revision of photoelectric effect. So photoelectric effect is the phenomenon of emission of electrons from a metal by incident electromagnetic radiation. So what does that mean? That means that if you have a metal, you have a lot of electrons inside that metals, right? So like here in this case, this block represents a metal and the negative signs that you see, they represent the electrons. Now, when you make an electromagnetic radiation incident on this metal. So here these red rays that you see, they represent the electromagnetic radiation, and when these electromagnetic radiation fall on the metal, and if the electromagnetic radiation or basically light has sufficient energy that it can knock off electrons from the metal. So that emission of electron is known as photoelectric effect. Now, it is not necessary that if the energy is always greater than the work function of the metal, then electrons must come out. Now here you might ask, what is work function? Now every metal has a work function. What is that? That means the minimum amount of energy that is needed to knock off an electron from the metal surface. So that is called work function. So every metal, so different metals have different work functions. So you know, it is like, the difficulty level is different for different metals to knock out an electron, because how much energy you need to reach that work function of the metal, that would depend on the value of work function of that particular metal. Correct? Now generally we denote work function by the letter phi. This denotes work function. And let us say that this incident radiation has energy E, okay? And let's say that this metal has a work function phi, okay? Now, when will the electrons get emitted? Now, if E is less than phi, that means the energy of the light, if at all that is less than the work function of the metal, then definitely there will be no photoelectric effect, because in that case it is not at all possible to knock off the electrons from the metal surface. Now, when there is a possibility for photoelectric effect to occur, only when the energy E, that is this energy of the incident light, is greater than the work function of the metal. Now, again, in this case also, it is not necessary that the electrons must come out if E is greater than phi. Why? Because now this energy which is given or which is incident on the metal, now that energy gets used up within the metal in many different ways. For example, it is possible that the electrons use the energy in collisions, because inside that metal there are so many electrons, right? So they will collide with each other. For collisions also they would need some energy. So there is a possibility they use up this energy for collisions. So in that case, what will happen? The entire energy will get used up in collisions. Now, if the electrons need to be emitted out, in that case, the electrons should have some energy, because when the electrons are emitted out, they have some kinetic energy, right? So some energy has to be left for the electrons to come out. Now, in case everything get used up for collisions within the metal, there will be no photoelectric emission. Okay. There is another option that the electrons near the surface may come out. So it might happen that there are some electrons which are located very deep inside. So those electrons would need all the more energy to actually come out, right? So there is a possibility that the electrons near the surface might come out, because there's a possibility that there was some energy E, some part of the energy was used up in collisions, but some part of energy is still remaining. So using that some part of remaining energy, the electrons near the surface might come out. So that's a second option. Okay, and what could be the third option? The third option could be that the electrons very economically use the energy. That means they do not waste energy in collisions and all of that. So they use the energy in the best possible way, and then they come out. So in that case, they will obviously come out, and even after coming out, they have lot of kinetic energy. So electrons come out, plus they have lot of kinetic energy, because they have utilized energy at its best. So they have so much of energy. So you see, in the first case, all the energy gets used up in collision, so the electrons can't come out at all. In the second case, there is a possibility that some part of the energy is used up in collisions and other activities, but some part of energy is still remaining. So as a result, the electrons near the surface might come out. And the third scenario is the electrons use the energy so effectively that they come out, plus they have some kinetic energy for themselves. Right? So these are the three possible scenarios that might happen when we make a light incident on a metal. Okay, now please understand that if energy of the incident radiation is less than phi, in that case photoelectric effect cannot take place. Okay, so now what we understand from all these three scenarios is this, that if at all the electrons which come out, now the electrons which come out, they are termed as the photoelectrons. So that's the name given to them. Now if at all these photoelectrons have some kinetic energy, then what is that kinetic energy going to be? So that kinetic energy would be nothing but the difference of this energy E and the work function, because as I said, only if there is excess energy than the work function, in that case only there is a possibility that the electrons might have some kinetic energy, right? So kinetic energy will be equal to E minus phi, correct? So or we can also say that the maximum kinetic energy, which we generally denote as K max, would be equal to, what is this energy E? So this energy is basically energy of the incident light, which we can write as H nu. And what is phi? Phi is nothing but work function. Now we can also write this equation in terms of the wavelength of the incident light. So we know that nu is equal to, nu which is the frequency of incident light, is equal to C by lambda. So this can also be written like this. So this equation is also known as the Einstein's photoelectric equation. And this equation has a lot of applications. So it is photoelectric equation. Now please understand this concept very carefully, because this photoelectric equation is very important, because in your NEET exam a lot of numericals come which are based on photoelectric equation. Okay, now let us quickly look at some of the important concepts of photoelectric effect. So first we will quickly review threshold frequency. So what is this threshold frequency? It is the minimum frequency of light for which photoelectric effect takes place. As I said that, you know, when light is incident on a metal, let's say this is the incident light and this is the metal. Now to make the electrons, you know, come out of the metal surface, it is needed that this light has some energy E which is sufficient to overcome the work function of the metal, which is phi. So it is quite obvious that this light should have some minimum frequency beyond which only the emission of electrons would take place. So that minimum frequency is called the threshold frequency. Threshold generally means something which is at the, you know, the minimum of what is required. That is threshold. So it is generally denoted by nu naught. So normally the frequency of incident light is nu, but when it is threshold frequency, it is nu naught. So we can say that for electrons to just come out, so we can say that for electrons to just come out, that means even though they do not have any kinetic energy after coming out, that is fine, but just for them to come out, it is needed that the energy of the incident radiation is at least equal to the work function. Only then this is possible, only then photoelectric effect is possible, right? So this energy is H into nu naught, because this is the minimum energy of the incident light for which photoelectric effect would take place. So this is equal to phi, or you can say that the threshold frequency is equal to phi by H, where phi is the work function of the metal and H is the Planck's constant. So that's threshold frequency. Now the wavelength corresponding to threshold frequency is called the threshold wavelength. And how will we determine threshold wavelength? That would be given by, so nu naught, which is threshold frequency, is equal to C by lambda naught, or we can say that lambda naught is equal to C divided by nu naught, which can be written as CH divided by phi. So this is how threshold frequency and threshold wavelength are linked to each other. So here you need to remember this, and you also need to remember this. Now let's move on to the next important concept, which is photocurrent. Now the moment photoelectrons are getting emitted, the flow of photoelectrons would constitute photocurrent, because as you know, wherever the electrons flow, it's like charge flow. So flow of charge constitutes current. So similarly here also, flow of photoelectrons constitutes photocurrent. When we try to understand the factors on which photocurrent depends, we perform a photoelectric experiment. And if we look at the setup of the photoelectric effect experiment, we see that in the setup we have a cathode and we have anode, like this. So this is a very rough diagram, and what is observed is when light is incident on the cathode, light of some certain frequencies incident on the cathode, such that it can overcome the work function of the metal. So in that case, what would happen? The electrons will be emitted and they would start moving towards the anode. So the electrons basically start getting deposited, or they start nearing the anode. So that's how it happens, and the flow of these electrons constitutes the photocurrent. So in a way we can say that photocurrent depends on the potential of the anode with respect to the cathode, because the more the potential difference, the more would be the flow of the electrons in between them. So now when you actually look at the variation of photocurrent with voltage, the variation looks somewhat like this. So this is how the graph looks like. So we see that initially as the value of voltage increases, or as you can say that as the value of the potential increases, the value of the current also increases. But after a certain point, the value of voltage still increases, but the current remains at the same value. So this current is known as saturation current, because it is a saturated value beyond which the current doesn't increase. So that's how the current varies with voltage. And it is also observed that there is a voltage, there is a value of voltage corresponding to which there is no current, right? So you see, if you look at this point, for this particular value of voltage, what is the corresponding value of current? It is 0. So this value of potential is known as the stopping potential. So all that we understand is the value of photocurrent changes with the value of potential. Now as potential increases, potential of anode with respect to cathode basically. So as that potential value increases, current also increases, and at a certain point it reaches the saturation value. Similarly, there is a particular value of the potential corresponding to which the current is 0. So in fact, if you look at this value of the potential, this is actually negative potential. So the value of the potential is negative, right? So this is called stopping potential. Now, if you want to find out a relationship between the stopping potential and, so this is how stopping potential is linked to photocurrent, because corresponding to the value of stopping potential, the photocurrent would be 0. There would be no current flow. Okay. And how is stopping potential related to the kinetic energy of the photoelectrons emitted? So this is how they are linked. So as I said that at V0, now this stopping potential is denoted by capital V0. Now at V0, the current stops, right? So even the fastest electron must stop. Right, so all the electrons must stop because the net current is 0. So we say that EV0 is equal to Kmax. So that means when the value of potential is V0, then charge into V0 would be the corresponding energy. So this energy becomes equal to the maximum kinetic energy of the photoelectron, and that is why the photoelectrons have to stop. Right, and we already knew from photoelectric equation that Kmax is equal to hc by lambda minus phi. So we can say that, as I said, that this EV0 is nothing but the potential energy corresponding to the stopping potential. Now since the potential energy and the kinetic energy, they equalize, therefore the electrons have to stop. Okay, so now from this equation we can say that V naught is equal to hc by lambda E minus phi by E. So this is how stopping potential and K max are linked to each other. Let us quickly look at some of the important points related to photoelectric effect. There exists a threshold frequency for every material below which no photoelectric effect takes place. So as I mentioned that if the frequency of the incident light is less than the threshold frequency, in that case the energy of the incident light would be less than the work function of the metal, and as a result photoelectric emission will not take place, right? So there has to be a there has to exist a threshold frequency for every material. Photocurrent is directly proportional to the intensity of incident light. Now as the intensity increases, the photocurrent also increases. So if you want to show this graphically, this is how it would look like. Now we have already seen that how the current varies with potential. So if this is current, this is potential. So this is how the current varies with potential, right? Now it has been observed that for different values of intensities of light, let's say this is I1, this is I2, this is I3. So these are the different values of saturation current for different intensities of light. So you see that the variation of photocurrent with potential remains the same. The variation is the same, but the values of the current is more for greater intensities of incident light. So we can say that the saturation current is directly proportional to intensity. Intensity increases, saturation current also increases. Intensity decreases, saturation current also decreases. We can also say that saturation current is found to be proportional to the intensity of incident radiations. Exactly, that's what we mentioned just now. Okay, now stopping potential is independent of the intensity of incident radiation. So stopping potential, that is the value of potential corresponding to which the photocurrent is equal to 0. So that stopping potential is not at all dependent on intensity. Even though the intensity increases or decreases, that doesn't have any impact on the value of stopping potential. Stopping potential and maximum kinetic energy of photoelectrons increases linearly with frequency. So you see, one simple thing that you need to understand here is when you talk about current, it depends on intensity of light. So more intensity of light means more photoelectrons getting emitted, so more current. Okay. When you talk about frequency, now when the frequency of light is more, then frequency doesn't have any impact on the photocurrent. But when the frequency is more, then the stopping potential is also more. That means the current would stop at a higher value of stopping potential. Similarly, the maximum kinetic energy of the photoelectrons would also be more. So understand this relation. When intensity is more, more electrons are getting emitted, so more current. When frequency is more, then the number of electrons that is getting emitted is not changing, but the maximum kinetic energy of the photoelectrons increases, right? So if you look at the Einstein's photoelectric equation, it is E V naught is equal to K max. So you see, stopping potential and maximum kinetic energy, they are directly proportional to each other, and this is equal to hc by lambda minus phi, or this is equal to h nu minus phi. Right? So here we see that they are dependent on frequency. So if the frequency changes, the maximum kinetic energy would change. If the frequency changes, the stopping potential would also change. Thank you. Please visit examfear.com for free quality education. You can learn with a simple 4-step learning process wherein you can watch video lessons, you can ask your questions, you can refer notes, and you can take a free online test. We have content for class 6 to 12 on physics, chemistry, mathematics, and biology along with practical videos. So please subscribe to our channel for daily updates. Thank you.